In this part of video, I'm going to tell you about the fast Fourier transform and from fast Fourier transform, how to find out the dominant frequency of the fluid flow. So just to give you an idea that I ran the 10 cycles here and then I ran 10 more cycles. I didn't show in the video, but I ran 10 more cycles also. So from here you can see the dominant frequency is 0.187 and from 20 cycles the dominant frequency is 0.180, and it means that if I go with the 40 or maybe 100 cycles, the data can be improved and we can get closer to the data from the experiment. So experiment data we get very closer. So you know that the stall number from the Shams mechanism fluid third edition. So from this reference, the stall number is 0.172. So experiment data is 0.172, and we are getting around that value, but little bit off. So the idea is that the point here is that if you record more cycles, then you can have the more accuracy. So I would recommend that you at least go for like 50 to 100 cycles. Okay. So anyhow, let me tell you the procedure. So you know that when we are solving, so we observe the two plots. Number one is the okay. So in this way, basically we have the around 20 cycles, and before it was 10 cycles. Okay, so anyhow, I saved the file. So how to get the data? So first of all, you have to open the Excel, and after opening Excel, you have to import the file. So that file is like from the text, and this is inside the left and drag. So I will do these things to both of the files, left and drag. Both files are exactly of same 20 cycles. Okay, so and also I told you that if you increase number of cycles, if you record more cycles, you will get the more accuracy. So I'm going to open lift coefficient and finish. Okay, so if I put the index here, so let's say it is increasing by factor of 1. So I can get the idea that how many values we have in this whole file for the data monitor for lift coefficient. So here we have the 804 entries, but for the 20 cycles it should be exactly 800. So I have to delete the first 4 entries from the file. So this file is here. So right click here and edit, and you have to delete the first 4 entries from here. So and then save. Simple. Okay. And then you have to go to the Fluent, and from the results you can see we have the FFT, fast Fourier transform, and you can use any file. For example, if I use the 0.1 file, and if I plot, you can see that the dominant frequency is around the let me click here, it's around 0.187. It's around 0.187. And if I take the second point and plot, this is around 0.181. Okay, now the third file, which is a 0.3, and plot, this is 0.187. And if I load the lift coefficient and plot, you can see it's a point, now it's close to 0.174. It's close to the 0.174. So from here we can see this is the one way that you can directly get the data from the graph. Second thing is that you can write down the file. You can write down the file in the text file, and from text file you can get the data from Excel. So write FFT. So let's say I say it's FFT of CL. Okay. And then open the again Excel, the same file, and from here I will from text file again same thing, and all files, this is the FFT CL, next and finish. Okay, so we can change the accuracy level of the number. So number formatting, format cells and numbers, and you can put more zeros here. Okay, so and also select this whole range. And what we have to do here is that the first is your frequency, but this frequency should be corresponding to the maximum value of the maximum spectral density. So from the conditional formatting in the home, click here, and you have to top bottom rules and then more rules, and here I want to select the top one, and in the format I'm going to make it bold, and I want to make the color red. So simply, so the first one value will be displayed here. This value is here, and this is showing as the 0.180667. So when it is written on the screen, it is 0.18000667, but if you take a look from the graph, this value is 0.174. So I will be relying on this value 0.174. So I can put that this value or frequency, the dominant frequency is 0.174. Okay, and now if you take a look on the external data, so external data says it's the 0.172, and if we go with the CFD, so from the CFDs runs, we have so for the coarse mesh and medium mesh with the time step 20 time steps, it's a 0.1735 and 0.1757 for the medium mesh. And with the medium mesh, which we used here, basically almost 20,000 cells. So for the coarse mesh, it's 0.175, and with the medium mesh, it's a 0.184. But now with this case, we have the more accurate data. It's a 0.174. So if I get the error, so this is the frequency 0.174, and this is from CFD, and from experiment, the experimental data is 0.172. So if I get the error, so error is equal to so two brackets 0.172 minus 0.174. I think we should be subtracting the larger value and minus then the smaller value, and then divided by the external data, which is 0.172, then close the bracket, multiply by 100, and that's all. Okay, so error is 1.16%. That is very, very low value. So error is only around 1%. So it means that with the medium mesh and time step of 40 time steps per cycle, we are almost getting data which is very close to the data we have from the experiments. This is one thing. So this is about the frequency, and the second thing is, so I will save this file. Maybe you can, okay, the whole process is given there, you can do it yourself. Okay, now I'm going to import drag coefficient, and the drag coefficient is over here. Again, we have to delete the first 4 data points. Okay, let me check how many data points we have. This is equal to 804. Okay, let me do it over here. So from text, okay, this looks nicer. Okay, so I will be deleting first 4 data points from here. Okay, this is the drag coefficient. So take all of these data points it is increasing to very high values. No, this is not okay. Basically, we are getting the few numbers from the time step also. So insert, and we should be formatting in a proper way. So drag coefficient, okay, and it's from the space. This seems okay. Okay. Okay, 1 minute. Things are getting a little bit confused. No problem. Okay. So this is the drag coefficient. Okay, now this is okay. So select all the values in the column, and but the first four data points should also be deleted. 1, 2, 3, 4. Okay, so we have to put the formatting, and so formulas, and here I have to use the average quantity. Okay, so average value of drag coefficient is 0.66, and why it is so? So let me check. Number one is that its value should be around 1.5. Okay, so I need to check the reference condition. So the diameter is 1, and the length is also 1, so depth is also 1. So we are going to put the area is equal to 1 meter square also. Viscosity is 0.0062. That's okay. Okay, so what I found here is that basically we are plotting the drag, not drag coefficient. And and for lift coefficient, we are plotting lift coefficient. Okay, so this is the lift coefficient, but if you take a look on the drag coefficient, it is a drag force basically. Okay, this is a drag force, and you know the formula, so this is a very easy thing. So we have the average drag value. So basically, let me give you idea that the drag coefficient is equal to drag force is equal to drag force divided by 1 upon 2 density times area times velocity squared. So we know velocity is 1, area is also 1, density also 1. So 1 into 1 into 1. So we have to simply multiply the drag force with the 2 to get the drag coefficient. Okay. So now go back to the Excel sheet and press is equal to sign. Select this column and multiply with the 2. So drag coefficient is 1.32. And now if you take a look on the data we have in the PPT file, you can see the drag coefficient from experimental data is 1.5, but from the CFD with the time step is equal to 40, and that is 0.1453. The drag coefficient is 1.33, and in the medium match is a 1.34. Right now it's a 1.321709. So it's almost close to the CFD from the previous cases. Okay, so stall number is better, but drag coefficient is little bit on the lower side. Okay, so in this video we basically I explained the procedure to find out the the dominant frequency, and from frequency we can find out the Stall number by multiplying frequency with the diameter, which is 1, and divided by the velocity, which is also 1. So in this case, Stall number and frequency, they are exactly same values. And also we determined the drag coefficient, which is right now is now 1.321. And we made the slight mistake while we were monitoring data for drag coefficient, and instead of drag coefficient we monitor the data for drag value. Okay, and the last thing which I want to show you is the root mean square lift coefficient. So if you average data for lift coefficient, it's a minus 0.5 to plus 0.5, and average quantity would be 0. So the root mean square value will give you some data. So let me show you this procedure also. So I'm going to import lift coefficient. Okay, so we have the data points over here, and so how many steps are there? There are 800 steps. Okay, so I'm going to make the square of every value. So this value, then power by 2. Okay, so square of every value. And then we have to add all these values and then get the average. So average would be the summation of all values divided by the number of values. And then finally we have to take the square root. Okay, so we have to put the formula for the average value, and the average value is like this. And then we have to take the square root, because we made the squares and then we took the average of squares. So take the square root to get the actual value. This is square root of this value. So the lift coefficient, the root mean square lift coefficient is equal to 0.3490002. But if you take a look on the values, and if you just take the average values, the average value is going to be the 0. Okay, so average value is almost 0. Okay, but if you take a root mean square, so root mean square value of CL, this is 0.3490. And if you take a look here, this is from the one reference, and in this reference you can see this is the CL root mean square. So for 150 Reynolds number, the value is around 0.35, and here we have the value 0.349. Okay, so 0.35 maybe 2 or maybe something like that, or 0.36, and here's a 0.349. So even the data from the other references are almost same. So here it might be 0.37 or 0.36, 0.36 maybe. Okay, at 150, 0.36, and we are getting almost 0.35. So root mean square of CL value is also confirming to the data from the different references, and so is the case with the coefficient of drag value and also the Stall number. So with this we conclude about the important parameters like Stall number, drag coefficient, lift coefficient, and you can also plot the different parameters, like you can plot the velocity vectors in this way. And if you change the scale, let's say to the 0.1, you can clearly see the vectors here. Maybe 0.5 will help. And the maximum velocity you can see is a 1.36. And if you draw the geometry also, so we can draw the geometry of circular cylinder. Okay, anyhow. And you can display like contours for pressure, and you can display contours for velocity, and contours for the vorticity magnitude. Okay, so to see the vorticity, we have to reduce the values. So we can start with the 10. If you don't get the vorticity, you can make it like 5. Then make it 2. And 1 would be very nice. And you can also try with the 0.1 and see what happens. No, this is not okay. And there are some other criteria also, like we have the Q criterion normalized value. So you can also use this this value. So this is showing the 0.9. So let's say we use the 0.1 or 0.5 or 0.5 and 0.9. So you have to play with the ranges. So no, we cannot do it. So simple lambda 2 criterion. So auto range. This is from minus 18 to plus 5.7. So minus 18 to 0. Minus 1 to plus 1. Okay, this is looking nice. So minus 2 to plus 2. Okay, minus 0.5 to plus 0.5. Okay, this seems more interesting. Okay, so there are the many things you can plot there, here and there, and you can get the different things from the simulation. You can also plot the control lines, and if you plot the velocity magnitude, and you can also change the way it is displayed. So usually speaking, I go with the arrow, and this gives you the sharper colors. So you can see the vortices very clearly. Okay, so by going through all these things, we have covered everything which is described in the starting of the workshop, that what we are going to cover in this whole exercise. So we covered these all things. We covered the drag and lift coefficients, stall number, animations, contour and vector plots. And we made the geometry, we made the mesh, we set up the case, run the case, and I told you that how to run the case. First, how many time steps, then how many time steps, how to save the data, and then how to post-process those data files. And we also made the animations, we got the left and drag coefficients, we got the frequency, everything we done. So now I hope that you know about that, how to work around with when the flow is transient, how to get the time step, how to get the data, how to post-process results. So thank you very much for watching this workshop, and see you next time.